Well, I think that it's time to start this first plenary session. The the presentation, all the presentation are have been will be recorded, and you can download later the presentation, of course. Well, it is a great pleasure to introduce such important scholar and friends, Jerome Sueur. Jerome Sueur is an assistant professor at the Museum of National at the Museum National d'Histoire Naturelle in Paris, France, where he leads a research group named EAR. He has been working for more than 10 years with ecoacoustics, with a particular interest with the soundscape of forests in both temperate and tropical climates. He has coined some acoustic indices, developed the R package Sueur, and organized with me, the first international Congress of Society. He is now trying to build interdisciplinary research, making connection between ecoacoustics, conservation, artificial intelligence, psychoacoustics, and musicology. So I think that there are no more words to spend about the quality and the reputation of Jerome. And the title of his presentation is Long-Term Ecoacoustics, a Plea for Slow Science. So please, Jerome, I think that is your time.
Sorry, can you see me? Yes, I had some difficulties to share my screen. I'll try again. Sorry, it's Zoom. I don't know what happened.
Okay.
Just do it again.
No problem, we try. Your voice is perfect.
Okay, but my
perfect.
Yes, but Zoom is doing strange things now. What is it doing? Okay, I open again my slides and try to share again. Okay. Share sound. High quality. Can you see it?
Yes. Yes.
Okay, good. Okay, so thank you very much, Amo, for this introduction, for the ecoacoustics and this personal introduction as well. And first, I would like actually to thank you back. Thank you, Almo, Gianni, David, Nadia, Gino, and Juicy for having made it. Congratulations, because it was so difficult. You had to face a unique situation. And so it was really a challenge to organize this meeting. I'm so happy to be with you, even in a virtual way, today. So it's really a great pleasure to a lot of noise here. Okay. So, and I would like also to thank you for inviting me to do a plenary talk, a long talk. And actually this raises a question of what is a long talk, what is a short talk, what is a long-term study, what is a short-term study. And when I wrote my abstract, it's a few months ago, now I thought that I just realized that I was running maybe too much, fighting against time, fighting against the clocks around. And I thought that it could be the time to try to slow down actually, to do some kind of slow research and stop to do fast research, trying to get fast results to be published quickly. And this goes with the idea of ecoacoustics that you mentioned in your introduction, that ecoacoustics aimed at doing long-term research, long-term monitoring. So I really thought, yes, we should try to slow down and to take more time and to extend our time of observation, of recording. So this is the main topic of my talk today, and I would like actually to introduce some projects that we have on the long term here in the Museum of Natural History in Paris, in the small research group that we have, which is named here for ecoacoustic research. So the first thing that I had to face is, but how long is a long research study actually? Is it as soon as you covered 1 year, a complete year, which is already a kind of challenge, or more than 1 year? Is it 2 years, 3 years, 4 years? When does start this long-term research? And I found actually a review by James Smith, who wrote in Trends in Ecology and Evolution about long-term research in ecology. And there is this distribution of the length of study in years in ecology that have been declared as long-term research. And as you see on this diagram, you can see that the minimum duration of long-term research in ecology was 5 years, and the longest one was 68 years. And the median was about 30 years. I was quite surprised actually that there were so long research programs. I mean, more than 40 years is a very long time. Oops, sorry, there are works in the next door. I hope that you do not hear it. So I looked a bit more specifically at ecoacoustics, at what has been published, and focusing on terrestrial ecoacoustics. I'm sorry, I'm not so much involved in marine ecoacoustics. And of course, I found the publication by Sueur that we evoked the memory, and Anne Axel, who in 2014 published a 4-year study that was held in Michigan in a deciduous forest close to a lake. And I think that is the one that is published so far, which is one of the longest one. It was spanning over 4 years, from 2009 to 2012. And here you have one of the results, which is a computation of the acoustic index that Stuart and Anne developed, the NDSI index. Now there are some ongoing projects on the long term. First, there is this Australian Acoustic Observatory that Paul Roux will introduce just afterwards this morning. There is the Ocean Project in Japan, the NEON Project in the USA, the MIT in collaboration with the Living Observatory is heading also a long-term project in the east coast of the USA. And there are probably other projects I might have missed. I'm sorry if I missed them, but actually there are not so many. And why? Because of course, conducting a long-term research is really a challenge for many reasons. The first reason is probably funding, research funding, because it's very difficult to get grants that extends over 5 years. Most of the grants, at least in France and in Europe, are over 3 or 5 years, if not only 1 year. So it's very difficult to have a long-term view in terms of money, just to say it shortly. Linked to that, there are issues, of course, linked to human resources. There are now much more short-term contracts in terms of research, in particular in Europe, that are less than 5 years. So just below this minimum duration of long-term research. And even so, if you have an academic position, the career of a researcher is usually less than 40 or 42 years. Again, for what I know here in France and in Europe. Of course, there are also many technical challenges. Just to say, how can you store years of data in particular audio data that are quite heavy? How do you manage them? And how do you use equipment over years? How do you maintain it? And when the warranty of equipment is, in most cases, less than 5 years again. So we always face with this 5-year limit. And of course, the outcomes, how can you get funding if you declare in your project that your first paper will be published in 15 or 20 years? That means if we are today, I would say my first paper will be published in 2036. It's not possible. So many challenges to try to run long-term research. But why do we need long-term research? Why do we need to do that? Actually, there are many ecological phenomena that which rhythm is on a slow pace. It's particularly the case of the very well known now climate change. It's a very fast event at the scale of the Earth's time scale, but it's a very long event when we refer to the time of research, as I said, that does not go further than five years. So, but ecoacoustics still can help in studying the impact of climate change on ecosystems. And that's why you, Almo, and Bernie wrote in a paper, in a seminal paper in biological conservation in 2016, declaring that ecoacoustics is a good tool, is a good approach to study the impact of climate change, because ecoacoustics can run long-term studies thanks to a power of sampling. A bit later, with Almo and Bernie again, we published another short paper alerting on the possible change in the soundscapes according to climate change. And this was illustrated by regular recording done by Bernie in Sugarloaf, a place close to where he lives in California. So between 2005 and 2019, and I know that Bernie now has recording from 2020 and 2021. And Bernie observed a reduction of the biophony and of the geophony, which seems to be linked to an increase of the ambient temperature and linked with the drought events that we know in California. So what are the more specific questions that we try to address here in our group relating ecoacoustics and climate change? So first, we would like to know how the triplet biophony, geophony, and anthropophony change with time, and so potentially with climate change. Then we can go down at the level of acoustic communities. How do these acoustic communities change? What are the changes about the dynamics according to, again, climate change? And again, getting down along the ecological scale, how do population seasonality and phenology change with climate change? Well, there are plenty of challenges to address these questions. The first is those I have just mentioned regarding long-term research. But the other main challenge is that we have confounding parameters, as climate change is not the only slow and global change occurring today. So that's one of the main difficulties that we have to face. So I would like to introduce two research that we conduct in parallel in two very different places in the world. One is localized in the mainland of France, here, so in Europe, and the other one is in South America, in France overseas, in French Guyana. So these sites are two forests, but that are drastically different, but both of them are very sensitive to climate change. On the left, you have, I would say, a cold forest, because the year average temperature is only 4 degrees. It is in the Jura, so east of France, and we record that forest since July 2018. On the right, you have a typical tropical wet forest with a year average temperature of 25 degrees, and we record this forest since February 2019. So we do this project in collaboration with local conservation programs, here with the Parc Naturel Régional du Haut-Jura, and for the tropical forest with the Réserve Naturelle des Nouragues. And our plan is to document the changes, the possible changes of the soundscape of these two forests over the long terms. So we plan to record them over 15 years, possibly more if we can. So let's start with the first forest, this cold forest. So just to remind you, it's in the east of France. It's close to Switzerland. So here is a satellite view. This is a rather small forest. The surface is only 3,300 hectares. I should have underlined it, but here is the forest patch. It's in the area of the Parc Naturel Régional du Haut-Jura. It's a highly protected area. There are different conservation rules over there that make this area a highly protected area. The central zone of this forest is a coniferous forest with a single tree species dominating the landscape. It's a European spruce. But with the climate change, the increase of temperature, there is also an increase of the population of European beech. So invading, I would say, the main habitat constituted by the European spruce. In this forest, you have a high level of diversity, in particular acoustic diversity, which is due to several birds, 44 passerine birds, but also 5 vocalizing mammals, an estimated number of stridulating and buzzing insects. We still need to do an inventory of these insects, but no amphibians. And in this among these vocalizing animals, we have several flagship species, iconic species for Western Europe, like the hazel grouse, the Western capercaillie, the three-toed woodpecker, the grey wolf, the Eurasian lynx, and the red deer. So that makes this site very special in terms of biodiversity. So what is the main scenario in terms of climate? To make it very, very simple, there would be, we expect, of course, an increase of temperature, an increase as well of rainfall, but a decrease of snowfall. So how will it impact the soundscape? We are expecting an increase of the geophony, due to, in particular, to the increase of rainfalls. We expect a decrease of the sounds produced by bird mountain species that are more or less specialized to cold weather, so like the citral finch. And oppositely, we wait for an increase of bird valley species, like the European blackbird, a very common bird in West Europe. And of course, we wait also for a change in the seasonality of the local populations and then communities. In particular, we wait for a sooner and longer spring bird chorus. So how do we document the soundscape of this forest? What was our sampling scheme? Here is a map of the forest. In green, you have the central zone with only spruce trees. What we did is that we placed 4 recorders that are marked here with a yellow circle. And we place these recorders to cover the forest. And we space them enough to avoid pseudo-replication. That means to avoid to record sounds more than, to record them only once per recorder. And as you could see, we try to avoid as well the human use of this landscape, which is indicated here by the forest road and ski trails. So for each spot, we installed a SM4 wildlife acoustic recorder. So we record 1 minute every 15 minutes. That means that for 1 year, we collect more than 140,000 stereo files. So it's more than 2,000 hours of recordings per year. And at the same time, we take very local weather data, the solar irradiance, the temperature, the relative humidity, so using weather sensors. And we also take regular pictures of the habitat, a picture every 3 hours, to have information about the vegetation, but also about the snow cover, the ground snow cover, which is difficult to estimate in other ways. The first thing that we did was to try to estimate how far our recorders were recording. To do that, we undertook propagation experiments using a loudspeaker at different distances away from the recorder, here in its central position and in different directions. I will not go into the details of the methods nor of the results, because Sylvain Hopper will detail all of this with this afternoon. So just to listen a bit this forest, I will play, I would say, a classical recording in this forest in the morning at springtime, close to summer. So let's start and see if it works. So it's a typical, I would say, European bird chorus, but it's quite rich, it's quite nice, it seems quiet and very rich. But the problem in this forest is that we have also these sounds. Okay, so other birds, but they are very present. Actually, here is on the left a map of the site. The site here in orange, and the recorders, and the center of the recorders are the the blue dots here. And you have an image of the flight path over the site for a single day. And for a year, you have more than 100,000 aircraft passing over the recorders. So we potentially have a huge pressure in terms of anthropophony. So the first goal that we had was to try to quantify this anthropophony level. To do that, we automatically identified the main 3 items that were identified in the field, that were aircraft noise, wind sound, rain sound, biophony, and when nothing is happening, silence. And so we use MFCC features to describe all the recordings over a year, and we gave the MFCC feature to a very simple artificial neural network, a perceptron, very basic ANN, to identify in each recording if there was an aircraft, noise, wind, rain, biophony, or silence. This work was achieved by Ellie Green-Fender. We will speak on Friday about soundscape definition and concepts. So here are the main results. We are quite confident in these results as the area under the curve of the rock curve were very high, around 0.9. So here is the relative abundance of each sound type. You see that in all the recordings that we collected over a complete year, we have 75% of files with at least a short time of aircraft noise. Then comes the biophony with 40%, which is still quite good, I would say. And then wind, 35%, rain, 21%, and then the remaining silence, only 12%. So you see that in this soundscape, the anthropophony through the aircraft noise is dominating. And then it's the geophony with the wind and rain, and then the biophony. If we look at more details using a multivariate analysis of this absence or presence detection results, we can see that the silence in the forest occurs when it's quite obvious, but it's good to see it and to have quantified it when there are no aircrafts, when there is no biophony, no rain and no wind. And this occurs mainly during winter. Here in green, you have the different months. So here you have mostly the fall and winter months. And in blue, you have the hour of recordings, and you see that it's mainly during the night, which was quite expected. When during spring and summer and during daytime, you have mostly the biophony, but also the aircraft sound. And so as a consequence, you have no silence. And we see that the geophony, the two main components of the geophony are correlated with no rain and no wind together and wind and rain together. If we look at the seasonality of these sound items, first regarding the aircraft sound, there is actually no seasons. I mean, tourism is active all the year long. Okay, so here you have the months from August to July because the program started in August. Then regarding the wind, there is a peak in March, and this was expected because this is known that in March wind is more strong. This is a wind local regime. If we look at rain now, there is no particular pattern except a kind of peak in December before snow arrives in January, February, and beginning of March. Then regarding the biophony, we have an expected pattern. So you have the less activity in the middle of the winter in January, then it increases with spring, with a peak in June, and then it decreases back in July, August, September, October, and November. So all expected results, but it was good to have been able to quantify them again. And the silence is almost regular all along the year. If we now look at the day and night phenology of these sound items, if we start again with the aircraft, we see that the aircraft activity is low in the middle of the night at 3 or 4 a.m. But as soon as 5 a.m., aircraft noises increases and goes up to a very high value, close to 100% of the files during the day, and does not stop until midnight. For the wind, we have a regime with an increase around 4 p.m. And for the rain, there is actually no specific pattern. The rain can occur at any time of the day. If we go to the biophony, we see that we have an expected pattern with very few activity during the night, but an increased activity when the sun rises. So at between 5 and 6, and then an increase up to 9, and then a regular activity during the day, and a decrease then until the night. And the silence shows an opposite out-of-phase pattern than biophony and aircraft, okay, with more silence during the night. So what is interesting here is that aircraft and biophony seems to follow exactly more or less the same pattern. they are quiet during the night and active during the day. And it makes sense because we are all diurnal animals. There are not so much nocturnal animals in this forest. And so the aircraft are at the same time than the biophony. And so it's out of phase with silence. So this suggests that aircraft noise is very important and might impact the biophony level. So with this study, we could classify and track automatically over a year the soundscape main components, and we did that at a rather low cost. We could reveal a high level of noise pollution and highlight a kind of discrepancy between high ground-based conservation rules and no air noise mitigation effort. So to make it very short, the message will be, we have a beautiful and rich landscape, but an ugly soundscape. So we do other study, as I said, we work also at the community level. So we aim at tracking the bird community, bird acoustic community, using a new index that was developed by Sylvain Aubert. And so we will track the day, year, and over-year phenology of the birds and the potential impacts of aircraft noise. We also work at the population level. So we are monitoring with Frédéric Seb, who is the PI of this more short-term project, the Western Capercaillie. Here is a recording done by Sylvain Aubert. And so we aim at estimating the seasonality, the population density, and again, the impact of aircraft noise. If you want to know more about population tracking, I invite you to follow the talk by Sarah Obeid on Friday. But we also try to change about how point of listening, not trying to work at the landscape, community or population level, but try to track ecological functions of the forest. And to do that, we focused first on flying insects that, when they fly, produce a buzz that can be recorded quite easily. These insects, when they fly, most of them fly and pollinate flowers. So the idea is that insect buzzing is an indirect indicator of pollination. Just to listen a sound of an overfly, which pollinates. So you can, it's very clear. And the second ecological function that we wanted to track was the one which is related to woodpeckers that make sounds when they drum on the trees, either for communicating or for foraging. And these woodpeckers reveal actually the state of the wood because their activity, drumming activity, is related to the age of the trees and also related to the occurrence of insects, of wood foraging insects like bark beetles. So we try to monitor pollination and wood state by recording buzzing and drumming sounds. So to do that, we use actually exactly the same data set that we use to estimate the different sound items of the soundscape. But here we use an artificial intelligence technique known as a convolutional neural network. So it's another type of artificial neural network based on image analysis. So we worked on the spectrogram that we pre-treated with some filtration and data augmentation, and then we pass them through a 5-layer CNN to get an output about the probability of occurrence of buzzing and drumming sounds. This work that was done by Alexandre Folio returned very nice results. So here are heat maps of the seasonality of the two sounds. So on the x-axis, you have the months, and the y-axis, you have the time of the day. And you can see that the buzzing is occurring mainly from June to late September, beginning of October, during the day. So the gray line are the sunrise and the sunset, and with two peaks of activity after sunrise and before sunset. For the drumming, most of the activity is during the day, but there are some drumming also during twilight and night, and there is a peak of activity in March. If we try to correlate these acoustic automatic detections with weather parameters, we can first try to connect them with solar irradiance, so with light basically. We see that buzzing, so that means indirectly pollination, occurs more during daylight. Here in gray, you have the light which is available in the forest, and in color, in blue, the distribution of the buzzing detection, so in relation with light. On the right is the same, but in red for the drumming sounds, and you see that the drumming sounds are slightly left skewed, with more activity at twilight or just after actually the sun rise, so rather low daylight conditions. If we link these detections with temperature, what do we have? We have, for the buzzing sounds, a shift, actually. A shift, you see that the buzzing sounds occur mainly at 20 degrees, which is not that much available in the habitats. And for the drumming, there is almost a perfect fit between the temperature available and the temperature used by the woodpeckers when they drum. So the idea here is that if there is a shift of plus 1.5 degrees, this is one of the scenarios for climate change, then it would probably benefit to pollinators, but impact negatively the woodpeckers. So to sum up with this project, it was possible to automatically classify ecological functions, again at a rather low cost. It was not that time demanding, and it was possible to estimate the climatic breadth of two ecological functions. And we could anticipate opposite response according to climate change. Now, let's travel and fly over the Atlantic and land on French Guiana. So it's a part of France between Suriname and Brazil. Over there, there is a huge tropical forest. A part of it is preserved in the Nourag Reserve. It's the largest reserve in France. It's more than 100,000 hectares. So over there, we have a field research station where we can conduct observations and experiments. Here is the forest. The forest is very rich. In the very small plot where we record, I will show you exactly what we do. We have more than 200 birds, 26 frog species, at least four mammals vocalizing, but excluding bats, an uncounted number of insects, and all this biodiversity is hidden in 172 tree species. So huge diversity as classical, I would say, in tropical environments. Just to give you an idea, here is a single recording of 1 minute, and we have birds, mammals, insects, and frogs. Let's try to listen to it, to take some time to listen to it. So these are the howler monkeys. So what about in terms of climate? What do we expect? We expect a decrease of rainfall, an increase of wind, and this would lead to a kind of savannization of the forest. And there will probably have changes in the rainy and dry season patterns. That means in terms of soundscapes, there would be changes in population seasonality, probably a decrease of the rainy season species populations, in particular frogs, that would lead to a rearrangement of acoustic communities and soundscapes. So here is the place where we settle our sampling protocol. We see that we have a particular facilities to go in the trees. Philippe Gaucher, a colleague of us, who is traveling in the air to install a microphone here at the top of the trees. So we define a kind of quiet zone, and we have a single recorder with two microphones, one which is settled at the understory level at 2 meters, and the other one in the canopy at 40 meters. And we couple this data with weather and atmospheric data that are gathered by a specific equipment managed by the CNRS. So over there, we did a similar propagation experiment to see how far we record. I will not go into the details again. Here is the very first results on that project. It's a heat map of a year of recording. On the x-axis, you have time from midnight to midnight, and on the y-axis, you have the weeks, successive weeks, so starting from January on the top and going back to December at the bottom. And we can clearly see, here it's in the canopy recordings, that there are specific patterns, probably more activity at different time of the day and different time of the year. And if we link it to the dry and wet seasons, we see that it seems that there is more activity during the dry seasons. So now our goal is to see how this pattern changes over years. We also run population monitoring. I do not go into the details, but we can follow the one toucan. I invite you to follow the talk by Manon Ducrotet. She will detail all of this. We followed another bird, the screaming pia, a very specific bird of the tropical forest. And we are also aiming at monitoring night birds, which are difficult to follow in usual way. So we will do it acoustically in collaboration with Christophe Thébault at the Université de Toulouse in France. But just to try to conclude, I think that we are trying to develop multi-level studies. So working both at the soundscape, community, and population level, but by including now also the monitoring and the study of ecological functions like pollination or wood state, but it could be for other functions. We also try to have a multi-tool approach using unsupervised technique, using machine learning techniques, supervised technique, artificial intelligence, and acoustic indices. So far we have short-term results because it's too early to have long-term results with some prediction on the long term. So far we did only quick ecoacoustics, but of course our goal is to do long-term ecoacoustic and therefore slow ecoacoustics. I'm sorry there is noise around. I can't do anything to stop that. I hope it doesn't disturb you too much. One way maybe to do slow ecoacoustics right now and not waiting 15 years is maybe to go back to the field and to take the time to listen what we record automatically and in a quite easy way, I would say. So the idea is to take the time to open our ears and to possibly find some musicality in nature sounds. And Armel Superbé will talk about this search of musicality in nature soundscape on Thursday. I thank you very much, grazie mille, for your attention, and sorry for the noise around. I'm of course open for any questions. Thank you very much.
Okay, thank you very much, Jerome. I think that your presentation has been extremely interesting for all. And I open discussion. We have not many time, but we have 5 minutes for discussion. And so I asked first the 2 panelists to raise their hand, eventually Sandra. Okay, Sandra, you can pose the question.
Hello, can you hear me? I
Yes.
maybe try to put my video on.
Yes.
Okay, thank you, Jerome, for this really great insight and for this excellent plea for slow ecoacoustics. And I would like to take the opportunity maybe to raise the issue if we can use this Congress to discuss maybe if we can join forces in setting up a network of long-term recorders. So maybe each of the groups who are more permanently involved in ecoacoustics can maybe spare 1 or 2 recorders. And we in Freiburg, we just set up 1 recorder that we aim to stay in a forest for long term without having additional funds. And what we maybe need is to discuss common methods so we can compare our results more easily, and a platform where we can share the data. So we don't have time to discuss it now, but maybe
Yes, I
time
totally
eventually.
agree. That's a very good point. Of course, trying to share and to work together with similar method, which is probably the most important thing, with kind of standardization in what we do, which is not as easy. And it's probably maybe the place to discuss that in terms of sampling, in terms of equipment, in terms of data sharing. But of course, if we can extend not only the time, but the space, it would be great. Yes, Sandra, yes, I agree.
Okay, thank you. And I have a question from Klaus Rede. Please, Rede, and Sandra. Okay, thank you.
Hello, everybody hears me?
Yeah.
And I try to, yeah.
Okay, please.
Okay, thank you, Jerome, for this beautiful talk. I like this idea of long-term recording. And just one suggestion, which has to do with Sandra Müller's proposal. I think it is important to mobilize recordings, old recordings, which are going back decades. For example, I found while working in Barrow, Colorado Island, I found references to tape recordings going back to the 1950s, 1960s. These are not all perfect soundscape recordings, and they are certainly not standardized, but they are going far back into history, and we always have this problem of shifting baselines in ecology. So I think to mobilize these old recordings would be an important task for the Ecoacoustic Society, and of course this needs digitization of tapes, it needs storage in memory institutions, like, for example, the Paris Museum, etc. But I think there's more around than we are aware of, and it would be very valuable to mobilize these old recordings. Thank you.
Yes, Klaus, I totally agree. We thought about that, but it's true that it's difficult in terms of standardization, of sampling, but it's true that there are plenty of recordings that are historical recordings that should be used. So we, as you said, we do that. We have an archive here in the museum. You have one in Berlin, London, and Cornell. And at some point, maybe there should be a kind of maybe international committee try to foster our efforts to save this data and to use them at the end. I agree with you. We should try to use them as museum specimens. It's the same process.
I have just a question from the attendees, a question from Guru Raya from India. Is the recording frequency limited below 20 kilohertz? Is there a possibility to increase it to include sounds from bats or frequencies behind human hearing?
Okay, so we do indeed focus on audible sounds, human audible sounds. So the sampling frequency is 44.1 kilohertz. The equipment we use does not allow to go higher. It goes up to 48, but we do not record in the ultrasound. It's mainly due to technical challenges because the level of data storage increases exponentially. And so we focus so far on the audible sounds, but of course you can go high in the high frequencies.
Okay, there is another question from the attendees by Tiago Dicudo. Is interested in this difference about understory and canopy soundscape.
Okay.
Yeah.
Yes, so we documented that some years ago. We did a comparison between understory and canopy, and there are differences. There are clear differences because there is a vertical stratification for mainly frogs and insects, and you can clearly hear it and see it on spectrograms. So that's why we use two microphones, so to sample at a low elevation and at a high elevation. There is a difference, clear difference.
Okay. There are no other questions at the moment. I think that I have a question directly for you, Jerome. I'm really interested in geophony. Recently, I recognized that geophony is the background in which animals are adapting their sounds, not only vegetation, but geophonies. Do you believe that new investigation in geophony, because today we are excluding geophony from biophony because we believe that they are creating problems. Indeed, geophony is part of a story in which vocal animals are engaged. So what do you think about in general? Not
yes, I totally agree. We know that, sorry for the noise, I don't know if you can hear it, but...
No, it's fine. It's fine.
Okay, for me it's very pleasant. So the wind and the rain, we know that they constrain a lot animal communication, acoustic communication. So it's clear that geophony has an impact on biophony. And what we did with our analysis in the Jura, in the cold forest, is that was interesting because we realized that actually the soundscape was dominated by geophony. That the sound of the wind and of the rain was almost the most important sounds in the soundscape, and that triggers the idea. Yes, we should not always take them apart, try to remove them, because they are really part of the soundscape, and for human being as well. For when we sense the soundscape, it's important to feel the wind and to hear the wind and the rain, or even the light sound of the snow falling on the trees. This is really part of the soundscape. So I agree with you that we should pay more attention to geophony indeed. Yeah. Okay,
thanks for your answer, and thanks for your presentation. It's time to moving in the next